Section 12.5 is actually one of the easiest sections. It's on symmetry, and we've talked a lot about symmetry already because we've talked about reflections. So the only reason why this isn't in the beginning of the chapter is because it also hits on rotations as well. So we'll revisit and reintroduce reflections and rotations, and we'll talk a little bit about graphing in the end and just say how they're symmetrical. So it'll be very little explanation and just a whole lot of examples just to make sure we hit them all. And we'll look for examples of symmetry in real-world applications. So that'll be a part of your summary as well as just some stuff. So symmetry, by definition, at least geometrically speaking, is isometric figures on opposite sides of a dividing line or about a fixed point. So basically, if I take a figure, if I take a pre-image and if I reflected it across a line, I've made some sort of symmetrical figure, or if I've rotated it about a fixed point, the image and pre-image also make a symmetrical figure. So they're two different kinds, and they're two isometric figures if you divide the line or take a fixed point with them. So I'll do two examples. One's a line or reflectional symmetry. They're both the same thing. It's if you reflect a pre-image over a line. So let me just draw something here. Let me give you like this right here. And I'll say, okay, so I have this pre-image. And if I reflect it over a line, so let's say I reflect it over this right here, I'll call it AB. This will be my line to reflect it over. Then I will create an isometry. So by flipping it like that, reflect it over, and boom, I've created pretty much a circle. So basically what it says is this figure has line symmetry. So this entire thing, the circle itself, this what I call pre-image and image here, they together create a circle, and this figure has line symmetry in that it divides right through here. Now, you'll know with a circle, or, I probably shouldn't have used a half circle in here because this will be the most extreme example of something that has both line and rotational symmetry. But a circle can be divided anywhere along its center. If I go through this line, and this line, and this line, etc., all of these are symmetrical through any of those lines. So again, probably not the best example to give right now, but we'll be going over some other ones in a second. Rotational symmetry is if I rotate a pre-image about a fixed point, and its isometry ends up being the same figure. So here's me kind of saying it the other way, where let's say I have I'm not going to use a circle this time. Let's use like a trapezoid or something. Okay. Let's use one that's specific to this. Let's use a parallelogram, which is specific to rotational symmetry. If I take a parallelogram, actually the way that I'm saying it with the definition is if I take a parallelogram and rotate it about a fixed point, so let's say I have this fixed point right here, and I want to rotate it about that. It has rotational symmetry in that, and that's not a perfect center right there. But if I take this and rotate it 180 degrees, like that, I end up with the same shape. So there's a fixed point that I can rotate about and make that possible. Now the other way that I wanted to put it is if I had this pre-image right here and made another image here by rotating it about that line that's about that point, but I'm not going to be talking about that. But so anyway, you can see that this image is the same as this image right here, and you have to say how many degrees of rotation that is. So watch where this green part goes. This is 90 degrees right here, this is 180 degrees right here, so it has rotational symmetry 180 degrees. Whenever you list something, it'll either be from 0 degrees to 180 degrees. You wouldn't say like 270 degrees like this, because that's the same thing as just saying 90 degrees counterclockwise. So you'd always list something 0 to 180 clockwise or counterclockwise. And point symmetry is a figure that has 180 degree rotational symmetry. So this parallelogram, for instance, has 180 degree rotation, so this has what's called point symmetry. So we'll go through some examples of both of these and just make sure that we divide them all and show them. So line symmetry and common shape. So here we have a square. And what are its axes of symmetry? Whoops. So the square, you can divide it right through the middle here, and none of these will be exact, but if I divide it right through the middle here, then I have a mirror image of this side and this side right there. So dividing this right in half, this way and this way, I should probably be more exact than that. This way and this way give it line symmetry. Okay, where else can you find it? How about hitting the corners? What if come on. This is quite a nuisance. What if I go from here to here? If you look here, I have a triangle. In fact, it's an isosceles right triangle. And here I have an isosceles right triangle, and they're both congruent. As long as you have congruent shapes, whenever you divide these, you have given it line symmetry. So there's another example right there. Here's an isosceles right triangle, which is half of that square right here. Now, I can't go this way and divide it in half and say I have line symmetry, because this is not an isometry of that side. So you have one right here that's an angle bisector, and as long as this angle and side are congruent to this angle and that side, and you've made congruent triangles, then you're golden. And I think this is the only place, looking at it, that will actually give me that. I don't think this gives me it this way, because this triangle is not congruent with that triangle. So you only have one line of symmetry right here. Here's a rectangle, so it doesn't have all congruent sides. So you have to check and see what would give it line symmetry. So for instance, we can still go up and down like this and pretend and assume like those are right down the middle. Actually, let me move that. I kind of have OCD with that kind of stuff. But I can't go this way and this way. And try and think about why. In fact, let me take away these lines just to show it again. If I divide this in half here, this is not a reflection of this. Yeah, the triangles are congruent, but they're not the same orientation. In fact, if you remember that term, orientation would imply that this short side right here would have a short side right here, and it would make, a kite. But in this case, this is not a kite, and so we can't say that this actually has line symmetry. So there are only two in this one, which are right here and right here. And you could practice some of these on your own. In this case, this upward arrow, just like the triangle, it only has one. It just divides right down the middle. I can't get one here and say it has reflectional symmetry, or across this way as well. So continuing practicing down here, we have a hexagon, and we can say, well, here's one that crosses through there. It divides into two trapezoids of the same orientation, and all of these actually divide them into trapezoids of the same orientation. If I go across here, here, and here, so going across all of the vertices, all of the corners of the vertices here. Now there are three other areas where I can get it right here. If I divide right down the middle, assuming that we're right down the middle, I create these weird-looking pentagonal shapes, like that, and then of course going through all of these as well. So it looks like we have multiple lines of symmetry. In this case, we actually have 6. So you'd have to count them out and say how many you have. If it ever asks you, how many lines of symmetry does it have? So let's try a pentagon as well. Now, a pentagon is not like a hexagon. I can't go. Now, I can go this way. I can go right down the middle and say, okay, I've made 2 quadrilaterals which are isometric. I'm sorry, which have, I should not have talked about before whether it had same or different orientation, because in this case, these two have different orientation. But in this case, these are reflectional. These have mirror images. Going this way does not make it reflectional, as you can see. Neither does going diagonally. Actually, I'm sorry. This does make it. This does give it reflectional line of symmetry. You can see right here it creates the same quadrilateral. So if I go across one vertice, I guess that's called a vertex. If I go across one vertex and divide it down to another side, I've given it another quadrilateral just like that top one. So this one has 5 lines of symmetry. Like so. And a circle, as I said before, it has an infinite number of lines of symmetry. If I create a center, which I'll go as closely as possible to a center right there, here's a line of symmetry, cuts the circle in half, here's a line of symmetry, cuts the circle in half, etc., etc., and I can do this forever. I can just keep going as long as it passes through the center, and I've made essentially a diameter, I've made a line of symmetry. So this has an infinite number. Okay, Okay, let's go to rotational symmetry and common shapes.